Hi guys, we're going to be learning about exponential functions and other functions this chapter. So here's our first topic, exponential functions. So I have attached this guided notes onto your Google Classroom where you can either print it out or copy it onto your notebook and write this along. That's going to help you with your note taking here. You want to have this written down so you can reference it when you're working on your problems. So I'm going to zoom in here. I do have some of the work on the side, but we're going to get to that in a second. And we're really focusing on the formula for this equation. So it's already in a box here, but I'm just going to kind of really show you what's going on here. So we have y equals a times b to the x. So when you're looking at this, you can tell that b is your base. That's always what your x as an exponent will be on. So think b base. It's what your x is an exponent on. Sometimes you'll see another number being multiplied to it, and that's our a. So a is going to change a couple things, just like how it did before when we were looking at transformations. A could change if it's stretched or compressed, how high it goes or how low it stays. So a is just a number, and sometimes we see it, sometimes we don't. If you don't see a number there, it's 1. So when we're looking at number 1 down here, my function is a of x, which is just like f of x, equals 3 to the x. So you can clearly see that 3 here, that's the number that has x as its exponent. So that means if I were to kind of expand this, and this isn't necessary, but it's just a way to see your work. If I were to expand this, I have a to the x equals, and it's really 1 times 3 to the x. And you can see that now that aligns with what we have in the box on the top, where our a value is 1. Okay, so our question is also to graph this. So our a value is 1. We can also label our b value. It doesn't really ask you, but if you can figure out one, you can determine the other. So our b value is 3. And to graph this, it's our good old-fashioned just make an input-output table. So if I was to graph number 1, I've already created my input-output table. So when I'm looking at this, there's one thing I want to draw your attention towards. So when you're looking at an exponential function, occasionally you will have negative exponents. So what you need to remember is that if a number has a negative exponent, it gets placed under 1, or it becomes its reciprocal. So this is really 3 over 1 to the second, and we would replace it, or we would switch it as 1 over 3 to the second. So that is a big note that you want to make sure you're writing down, that if you have a negative exponent, that means to flip your number. So we had 3 to the negative 2, so that became 1 over 3 to the second, which becomes 1 over 9. And you can see the same thing happen down here with our negative 1. We had 3 to the negative 1, which became 1 over 3 to the 1, which became 1/3. So this is a lot of taking your time, plugging in your numbers. Also remember that anything to the 0 power is 1. That's another exponential property we've learned, that anything to the 0 power is 1. So this could be 3012 to the 0, and your answer would still be 1. So anything to the 0 power is 1. So you can see we use the rest of our exponents. We have our values here. So let's sketch this graph. So I'm just going to put a few important values on our graph because we're going to put a couple graphs on here. So let me put some notch marks for us. So when we're looking here, maybe we'll go up to like 6. Oh, we could fit more. So 6, 7, 8, 9, 10. We'll do 10. 9, 10. We'll do it on all sides here. And the left. Alright, so there we go. So each notch mark does equal 1. So we'll just put that in there so you know that those are 1s. And we're going to just put our first points on there. So I don't think I'll be able to fit both. So we had our first point was -2 and 1/9. So I'm going to go over to -2 up to 1/9. So it's just barely above. You're going to see that you're going to have to estimate a lot with these really small fractions. And then we had -1 1/3. So it's just a little bit higher. We had 0 1. We have 1 3 and 2 9. So you can see that our steps between each point, they're getting bigger, they're growing, they're kind of like jumping really far ahead. So if I connect these points, you can see that this is not just a straight line. You can see that it's curved, and you can see that the change between the points is different, right? We're moving at exponential rates. So you might have heard that before, and now this is what you can tell it means, that at first it's a small change, but then the change kind of grows and gets bigger. So it's called like an exponential growth. And we're going to talk about that in a few minutes. So let's look at another one of the examples on this front page. So we have 2 times 3 to the x. So now that we're looking at this, this is already, and I'm looking at number 2 here, this is already in our, we can call it standard form. We can figure out what a is and also what b is. So a is the number that's being multiplied in the front. So our a is going to be 2, and our b is our base. It's the number that has the exponent on it. So our b is going to be 3. So I also made this table ahead of time for us so we can just look at it. You can see that it's still just your orders of operations. You need to do your exponent first and then multiply. So to show you the difference here of where are the errors. So this is an error analysis. So keeping an eye on this will also help you not to make these errors in your work. You're going to be aware of them. So here's 2 different ways I could work on this little piece here. If I had 2 times 3 to the negative 2 and 2 times 3 negative 2, we're going to do one the correct way and one the wrong way. So the correct way is to do your exponents first. So that means I'm going to do 3 to the negative 2 first, which this will now become 2 times 1/9. And we did 3 to the negative 2 above, so you can go back and see the work for that. And then you multiply and you get 2/9. So that is the correct way. This is correct. So now an incorrect way would be to do your multiplying first. That is not your order of operations. You have to do your exponents, then multiplying. So this is an incorrect method, is by multiplying first and getting 6 to the negative 2. And then that becomes 1 over 6 squared, which is 1 over 36. And you can really see here that these are not the same values. So this is incorrect. Okay, so you do not want to do your multiplying first. You can see that just by showing you that one little example, it's wrong. And then you're going to do all your work wrong. So just take your time, do it correct from the get-go, do your exponents first, then multiply. And if there's a number being added or subtracted on, that goes after your multiplying. So you want to make sure you're doing your exponents, then multiplying. I cannot stress that enough. So let's look back on, and you can see the rest of our values here. You plug them in, you multiply times 2. So we're going to go back, and I'm going to graph this function on the same coordinate plane that I did the first one. So we had our first value was negative 2 and 2/9. So it's just a little bit above, and I'll do this one in a different color. So we have negative 2 and 2/9. We had negative 1 and 2/3. We had 0, 2 was our next point. We had 1, 6, 3, 4, 5, 6. And then we had 2, 18. That's really not going to fit on our graph here, so we'll just leave it at this. Okay, and it's going to keep going up. It's not going to hit a value at 2 until it passes 10. So it's going to keep going up. It's going to keep going here. You're going to notice that these do not go below the x-axis. Okay, so they do not go below x-axis. This means that you have what's called an asymptote. Okay, if you remember that word, it's an imaginary line. It's going to approach, never cross over. So you can see that our pink line, and we'll label these now so we can look at these. Our pink line was just our first function, which was a of x equals 3 to the x. And the green function was similar, but there was a little bit different here. It was b of x equals 2 times 3 to the x. And you can either see it with parentheses or with a dot. So what do you think that 2 changed? I want you to think back to transformations. So our questions down here are, how does increasing the value of a change the graph? So think back to just transformations. When your a value is larger, it is stretching your graph. Okay, so stretching vertically. It's kind of like tugging the ropes, right? Tugging the end of the ropes, pulling them apart from each other. Okay, so in the same idea, what would making that value smaller? How would that affect our graph? Think back to any transformations we have. When that a value is a decimal or a fraction, it compresses. So this is, we're going to write compress vertically. All right, so on to page 2, you're going to see that now some of your a's and b's might be negative. So let's look at just these equations right here and try to see if we can determine our a's and our b's. So looking at number 5, I can see that the way that I would like you guys to break this up with number 5 is that your f of x is really just 1 times 2 to the x. So that means our b, our base, is 2 because we have 2 to the x. That means that our a value is 1. Now at the same time, I'm going to look at number 6. So looking at number 6, I can break this one up. This one's a g. So g of x equals negative 1 times 2 to the x. All right, so there's a difference here. You can see now your a is negative 1. So we're going to write that below. And your b is still 2. Your base is 2. But now we're going to take that and multiply it by negative 1. So I want you to kind of guess what's going to happen here. If you think back to your transformations, what would have happened in the past when your a was negative 1? How did that affect your graphs? How did that affect a parabola? How did that affect a cubic function? It flipped it over. So you're going to see that same thing here where they're going to get flipped over the x-axis. So I have the work on the side over here. And you can see this is just like our problem from the first page. You're going to plug in, these are the values you're always going to plug in, or you'll have a worksheet that has it already labeled for you, your inputs. So these are usually given. If not, you just use these simple values. Okay, so they're usually given, you plug them into your x's, and you evaluate. So input-output table. Once you have your points, we're going to put them on our graph. So I'm going to make my graph just go up to, let's see, we need it to go up to 5 in all directions. One, two, three, four, 5. Here we go. Oh, got a little messy. All right, close enough. So we have our first point was at, for number 5, was at negative 2 and, what was it? Negative 2 and 1/4. So if I go to negative 2, go up to 1/4, put a little dot. Again, you're going to have to estimate a lot with the fractions. They're going to get a little challenging. Negative 1, we had 1/2. At 0, we had 1. At 1, we had 2. And at 2, we had 4. So again, you can see that this is curved. You can see that it's growing. It's getting larger. It's making bigger gaps, right? We have little jumps, then a bigger jump, then a bigger jump, then a bigger jump, and it's just going to keep getting bigger. Again, that's what it means to grow exponentially. So now let's look at our second equation. So number 6, we talked about how with number 6, your a was negative 1. So when your a is negative 1, or if you have any other number for your a, just like on the front page, what you're going to do is you work on your exponent first, then multiply it by negative 1. So I would do 2 to the negative 2, which we have above, which was 1/4, and then 1/4 times negative 1, so negative 1/4. Do it again. So 2 to the negative 1 is 1/2 times negative 1, negative 1/2. So again, you need to do your exponent first, then multiply. Exponent first, then multiply. And you can see that you have negative 1, negative 2, negative 4. So let's graph this. Oops, where did we go? All right, here we go. So we have our first point was negative 2. Now our output was negative 1/4. And then I had negative 1, 1, negative 1/2. I have 0, negative 1, 1, negative 2, and 2, negative 4. Now you can clearly see that now this is turned upside down, okay? It's mirroring our original function because it's reflected. It got a negative a was placed in front, so it got reflected over the x-axis. So that's really what we can talk about is a negative a. So what I want you to do for these questions, obviously increasing the value of b, that's just going to make your graph increase faster. So this is just going to make your graph increase faster. Now, as far as making the value of b negative, I want to change this question to say making the value of a negative, because that's how we always remember this. A always changes if it's stretched, compressed, or reflected. So when a is negative, our graph is reflected over the x-axis. Okay, so keep that in mind. When you see a negative, you can expect it to look upside down. All right, so there's a couple more examples on this page. What I want to just highlight down here is that if your base is a number larger than 1, so we're looking at number 9 and this first statement down here, they go hand in hand. So our base is 2. It's something greater than 1. That means that if I were to have these like basic points, I'm just going to do real simple ones here. Okay, so if I had the point, let's see, so we have 2 to the x. We actually have this above. So we have negative 1, 1/2. We have 0, 1, and 1, 2. We'll just use those simple values right there. We could do 2, 4 if you want. All right, so that's our original one. Now let's look at when our base is 1/2 or 0.5. You can have fractions and decimals. Okay, so this one I'm going to do 2 stars. So this graph is going to help us answer the second statement down here. Okay, so when our graph has a decimal or a fraction as your base, let's look at what our input-output table would look like. So I'll just draw this on this white space. So we have, and I'm going to use a fraction here. Instead of 0.5, I'm going to change it to a fraction. You can leave it a decimal and just plug it in your calculator. So we have x, we have 1/2 to the x, and then we'll have y. So like I said, if there's no numbers, if there's no inputs for you, you can just put -2, -1, 0, 1, and 2. We're going to plug these in. So now we have 1/2 to the -2. So remember what that negative means. It means I'm going to flip it over. So now I really have 2 to the second. When I flip it, it becomes a positive exponent, but the number stays. So it becomes 2 to the second. I'll make this bigger. And that's 4. Let's do the same thing with -1. So I have 1/2 to the -1, which means I'm going to flip it. So now I have 2 to the 1, 2. 1/2 to the 0. This one should always be pretty easy because anything to the 0 power is 1. 1/2 to the 1. Anything to the first power is itself, so that's a 1/2. And then we have 1/2 squared. So might have been a while since you've squared a fraction. What you have to do is you square the top and square the bottom. So I really have that 1/4. So let's graph these. So now at -2, instead of it being like a low decimal, we're going to be up high. We're going to be at 4. So I'm going to change the color here. So we're going to be at -2, 4. And then we're going to have -1, 2. We have 0, 1, 1, 1/2, and 2, 1, 4. So when I connect these, it looks a lot different now. The shape is similar, but instead of it growing as we go left to right, if we had our little man, okay, remember your little man, he's still here. He didn't go anywhere. So as we go left to right, he's going upwards on our first graph, which was just 2 to the x. Our second graph, if we put our little man, he's going down. So you can see the difference here. Our second graph was when we had a decimal as our base. So this was the f of x equals 1/2 to the x, or the 0.5 to the x. And the green one was 2 to the x. Okay, so we can use this to kind of get those two statements filled out. When our b value was 2, it's growing. So that means when our b value is greater than 1, it's called exponential growth. Okay, so the exponential graph, we can just write grows. Okay, because we call that growth. And then when we look at our pink curve, when our base was 1/2, our little man's now going down. So we're going to use the opposite of growth, which is called decay. So if your base is a decimal or fraction between 0 and 1, the exponential graph decays. That just means that it's going down. So growth means that it's going upwards, left to right. Decay means that it's going down. All right, so just a few wrap-up check questions here to make sure that we're getting all the facets of this under our belt. We can match graphs. So we're going to start with this one. So when you're trying to match, the first thing you need to remember is that if you're plugging in 0, your base becomes whatever that number is to the 0. And anything to the 0 power is 1. So for instance, if I were to be looking at number 1, and I'm just going to do a little bit of side work up top. So if I had 2 times 1.2 to the 0, that means I would have 2 times 1, which is 2. So I know that number 1 is going to have the point 0, 2. It's an input, output. I inputted 0, output 2. So if you look, I actually have two functions that have this point 0, 2. And those two functions are either number 1 or 2. So I don't know which one's which yet. So I'm just going to write C or D. C or D. So I can kind of like start eliminating unnecessary answers. Now let's look at number 3 and 4. Now numbers 3 and 4, if I were to plug in 0, I have 4 times 1.2 to the 0. It's a different problem here. So then I have 4 times 1, which is 4. So now this gave me the point 0, 4. And if you look at number 4, you would get the same thing. So this one, number 4, and number 3, they both pass through that point 0, 4. So that could be A or B. So here we go. We're just kind of like simplifying our answer options here. So let's look at 3 and 4 first, because this is what we talked about last. If your base is greater than 1, it's growth. If your base is less than 1, it's decay. So looking at the curve of B, so I'm going to draw my little man. He helps me out a lot here. So if I'm looking at B, and here's my little man, he's walking upwards. So I know that that means that this is growth. So if I'm looking down at my equations for 3 and 4, growth means that B, my B value, is greater than 1. So looking at my options, I have 1.2 and 0.8. So 1.2 is greater than 1, which means that this is going to be growth, which means that it'll be option B. So I can cross out option A, because if we look at option A, we put our little man, he's walking downwards, and we know that's what's called decay. And decay means that 0 and 1, that's what your base is going to be between. It's going to be between 0 and 1. So that means when I look at 0.8, that follows that rule. That's saying 0.8 is between 0 and 1. It passes through the point I need it to. So number 4, my answer is A. So let's cross that out. We're going to give those little guys a circle. Halfway done. Now let's look at our first ones. So these are both growth. If I look at C and D, they're both growth, which can make this a little confusing because we put our little man, growth. Put our little man, he is growing again. Oops, there we go. All right, so that didn't really help us with anything. Now we can look at our equations and see what the small differences are. We have 1.2 and 1.9. So when you have a value of a base and it's larger than another value, but everything else is the same. We have 2, we have to the x, but we have 1.9 versus 1.2. The larger number is going to go higher, faster. So if I'm following along, and you can pretend like maybe this is a roller coaster. If I'm following along, and right now I'm following along on line D, it's kind of taking its time. It's slowly growing. Eventually I'm getting up to these points. and I get there. When I follow line C, I'm going, and all of a sudden it turns, and now I'm shooting upwards, kind of like King Ka, if you've ever been on that. So when it's growing faster, that means that our base was a larger value. So that means that this line here, C, that's going to correspond with number 2 because it had 1.9. So we can cross off D, we know this is C. And then just by process of elimination, that means that D is our answer for number 1. All right, we're going to use the same idea of being able to determine growth or decay and our B values. So this is a little chart that maybe you will see in a science class, in chemistry. This one's about of sodium and basically the count of sodium as time passes. So this is like a real life study. Visually looking at this, if you were to put your little man, I could absolutely tell that this is decay. If these were values that you were counting, your values are going down, okay? So that's how you can tell that this is decay. So if you put your little man, we did this earlier, he's going downward, so this is decay. So for number 5, we can circle B. It is decay. Now, we've talked about this. Decay means that 0 is less than B, which is less than 1. So looking at number 6, they're saying which could be true about the value of B. We've already answered it. We know it has to be between 0 and 1 for it to be decay. Don't be tricked about solutions like this because part B and part D, so this piece and this piece, are both semi-correct because B is less than 1. Oh, I correct myself there. I looked a little closer. D is not correct. That's saying B is less than 0. It's not. Okay, so it's between 0 and 1. It's greater than 0, but less than 1. This is a trick right here. Okay, because you need the whole thing. So let's look at number 7. Again, another multiple choice. Now, let's think back what happened. When did we have a function that got flipped over? It got flipped over when A was negative. So if I'm looking at all of my options here, my only possible solution would be C, because a negative value for A will flip it over. So negative value for A will reflect graph over the x-axis. Okay, so keep that in mind. Whenever it's reflected, whenever it looks like it's going downwards, that's actually just a negative A. It's not necessarily decay here. All right, last page, last couple of little questions that we can work on together before you do your practice assignments. So let me zoom in here. So for number 8, which of the following is a true statement? So let's start from the top and cross them off. So equation A has a B value greater than 1. So if I'm looking at the curve for A, my little man's walking downwards. So that's not true. Let's cross that out. It would be true if it said 0 was less than B, which is less than 1, which it does not say. All right, option B, the value of A in equation C is less than the value of A in equation D. Okay, so that's a tricky one here. That's also not a true statement. So the value of A for any function you can find by the point of the y-intercept. So right here, that's going to be our A value. So that's a little trick you can remember for yourself, is that whatever value you have there, so right now we have 0, 1, that means that that's the value of 0A. A in our case for all 4 of these curves is 1. So nope, B is not a correct answer either. Let's cross that out. Apparently I'm not a good crosser outer. There we go. All right, so equation B has a value of base B, where 0 is less than B, which is less than 1. Let's look at B. So using my little man, he's walking downwards, which means that is decay, which means that our B value is less than 1 but greater than 0. So that looks like a pretty good statement. I'm going to circle that one because it is true. So that means that D is obviously not an option. So equation B showed decay. Decay means that our B base value is between 0 and 1. All right. Okay, so these are two graphs that are mirror images. So looking at number 9, what's the value of b, little b, that's our base b for this f of x? Super easy, look for the value that is under the exponent, so 1/2. And then for the same thing for number 10, 2. It's our base. Little b is our base. So what is the relationship between the value of b and the two equations? Hopefully you figured out that 2 and 1/2 are reciprocals. So they are reciprocals. Okay, we've talked about this. This is when numbers get flipped over. So if I were to flip 1/2 over, I would get 2/1, which is 2. All right, and I believe that's it for that graph. Number 12, if p of x was 4 to the x, we want to let p of x equal 4 to the x. If r of x is created by reflecting it over the y-axis, what is the equation? So this is a little tricky. You wouldn't have to do something like this on your own, but we can use the same concept from numbers 9 and 12. We're going to have two functions here. We're going to have r of x and p of x. We already know what p of x is. It's 4 to the x. They're telling us that. So r to the x is going to be when we take the reciprocal of the base. So 1/4 to the x. So all we did was take reciprocal. Oops, that got a little messy. There you go, reciprocal of base. All right, last couple. These are super easy, so we just need to figure out if it's growth or decay. So one last time for you to remember how that goes. So if it's growth, our b value is greater than 1. And if it's decay, our b value is between 0 and 1. So it's a fraction or a decimal between 0 and 1. So all we have to do is look at our base. So looking at number 13, our base is 0.6. That's between 0 and 1. So number 13 is B. So we're going to make this a little bit easier. So I highlighted the correct answer. For number 14, our base is 1.6. 1.6 is greater than 1. So that means that this is now growth. And for number 15, this one looks tricky because you see a couple of decimals here, but you only care about the base. So 1.6 to the x is our base. 1.6 is greater than 1, which means that this is growth.